Hello, and welcome to the Academy of Useless Ideas. Calculus is undoubtedly a powerful tool for solving real-world problems, from designing skyscrapers to modeling the behavior of subatomic particles. However, in the Academy of Useless Ideas, we are not interested in those grandiose applications. Instead, our goal is to gain a deeper appreciation for the beauty and elegance of the mathematical theory of calculus by exploring its abstract and useless foundations. The area of mathematics that studies the foundations of calculus is known as real analysis. In real analysis, we ask pointless questions like, what exactly is a real number, and why do we need them for calculus? Have you ever stopped to ponder how you would define a real number? Surprisingly, after centuries of using real numbers, mathematicians realized in the late 1800s that they lacked a clear definition. Defining a real number turned out to be more philosophical than expected. However, it wasn't long before they realized that what a number is doesn't matter as much as how it's used in the practice of mathematics. To study the real numbers, we will rely on the axiomatic method. This method has been the standard approach to formalizing mathematics since Euclid's Elements. Instead of defining a mathematical object, the axiomatic method describes its behavior using self-evident truths called axioms. By using these axioms and the rules of logic, mathematicians can derive new truths about the mathematical object of interest. Those new truths are called theorems, while the process of asserting the validity of new theorems is called a proof. The axiomatic method allows mathematicians to explore the fundamental properties of numbers and their operations without being bogged down by the philosophical complexities of defining them. While the axiomatic method has been successful in formalizing mathematics, it is important to understand that the goal of mathematics is not simply to prove theorems. In fact, viewing mathematicians solely as people who prove theorems is akin to viewing meteorologists solely as people who use barometers. The true goal of mathematics is to gain a deep understanding of mathematical objects and their properties. Proofs are simply the tools that mathematicians use to ensure that their understanding is correct and not based on false assumptions or misconceptions. Rather than being the end goal, proofs are a means to an end in mathematics, a way of verifying that our reasoning is sound and our conclusions are correct. One of the most significant accomplishments of the axiomatic method is the arithmetization of analysis, which involves constructing the real numbers from the natural numbers. This process begins with the Peano axioms, which describe the natural numbers and their operations of addition and multiplication. The next step is to extend the natural numbers to include negative numbers, resulting in the set of integers. From there, the rational numbers are constructed as an extension of the integers in which every non-zero number has a multiplicative inverse. Finally, the real numbers are constructed as a completion of the rational numbers, allowing for the concepts of continuity and limits that are fundamental to calculus. Constructing each number system by building on the previous one offers the advantage of reducing the number of axioms needed. Mathematicians strive to use the smallest set of axioms possible, since additional unnecessary axioms can create inconsistencies in the system. However, starting with a minimal set of axioms also means that many things that seem quote-unquote obvious require proof. For example, if you start with the Peano axioms, we need to prove the commutativity of addition. As a compromise, under the understanding that it's possible to construct the rational numbers from the natural numbers, we will begin our study assuming familiarity with the rational numbers, and we will demonstrate why they are insufficient for developing calculus. This will motivate the introduction of the real numbers as an extension of the rationals, but with an additional property that makes calculus possible.